Okay, so we are starting with 22, working with 22, which is our nucleus section. Remember, with our nucleus section, it's really important to use these facts. This is these constant values at the beginning of the data booklet. They may well be important, so remember to use those. We also have the formula E is equal to mc squared, which we can sometimes need to use. Okay, so let's look at question 22. Which of the following decay sequences would result in the daughter nucleus having the same proton number as the parent nucleus? So, firstly, just to understand the different types, let's have a look at gamma. Gamma is the release of a high energy light particle. It doesn't actually change the charge of any of the particles inside, but it just leads to a lowering of the energy of the nucleus. Where with alpha, I'll just use the two examples here. If we've got an alpha particle, if we've got a nucleus, and say it's like that, and we have alpha decay, it decays by means of alpha. This is actually a 2+. It's got 2 protons and 2 neutrons, 4 nucleons. So this actually, when we balance it out, would be 18 and 36. So we see that our proton number would decrease by 2. Now with the beta decay, let's have a look at something here. Let's say we got W and we got 20 and 40. By beta decay, what actually happens is that you get this beta particle is actually an electron. So to get here, if we get conservation of charge, we've got a -1 there. This must become positive 21, so it actually adds a positive charge to your daughter nucleus. And what actually takes place, the number of nucleons stays the same, but one of the neutrons actually changes into a proton. So this is going to lead to an increase in the number of protons. So this would be correct here, that an alpha followed by a beta and followed by another beta would be the correct answer for that. Okay, so that's 22. Going on to 23, the difference between the mass of a carbon-12 nucleus, so carbon-12 nucleus, and the sum of the masses of its individual nucleons is 0.1 U. Which of the following is approximately the binding energy of the nucleus? Well, we're looking at the binding energy of the total nucleus, not of the individual nucleons. So overall, we've got 0.1 U, which is the energy, the binding energy. So we need to just come over here and come to U, and here we have this over here. We have 931 MeV C to the -2. Now, you don't really have to, if I can just explain this, let me just explain this a bit. You've got 931 MeV C to the -2. Now, this comes from this formula over here, that E is equal to mc squared. So when this is your energy, when I put it in, this c squared cancels with that. So your energy of 1 U is actually 931 MeV. So 0.1 would obviously therefore be about 93.1 MeV. And so it would be this one over here. Okay. Good. So we can go on here and we can go down to our next page. Alright, 24. The process by which a heavy nucleus splits into 2 lighter nuclei is known as, I hope everybody would get this right, that it would be fission. Fusion is when you join lighter nuclei to form more heavier ones. I mean, these are not correct. So that's 24A. 25. Which of the following correctly shows a renewable and a non-renewable source of energy? So here we're going into Unit 8, and perhaps before I start on it, I should just make sure that I get to my correct, because we'll be using these formulas quite a lot, I think, for Unit 8. And you really need to know what all of these different terms stand for. It's very important that you do. We're going to be using some of them now, so let's see how you do. Okay, so firstly for 25, which of the following correctly shows a renewable and a non-renewable source of energy? So oil is definitely not renewable, so that's not correct. Wind is renewable. Biofuel is also renewable, so it's not that. Ocean waves is and non-renewable, so it looks like C would definitely be the correct one. Both of the natural gas is not, so C would be correct there. That's pretty straightforward. So those two questions so far were easy on this page. We now are going to go on to the next question, and it is 26. It says critical mass refers to the amount of fissile material that will allow fission to be sustained. That is correct. We use that idea of critical mass. When you have got critical mass, then a nuclear reaction can take place. A chain reaction can take place, not necessarily a growing chain reaction. That's the starting off point of it. 27. The annual variations of solar power incident per unit area at a particular point on the Earth's surface is mainly due to the change in, and this is this over here, the tilt of the Earth. So, for instance, if you've got the Earth and it's tilted like that way, and here's the sun, and this is the point that I'm dealing with over here. Then we see that the sun's rays are spread over a large amount, and so you're not getting. But if it's dealing this way, it's been tilted now A, and now it will get the direct sunlight. So this B is correct.